may be familiar with the raster calculator, but not with map algebra. They're essentially fairly equivalent in terms of their functionality, just slightly different approaches. So the final thing that we'd like to cover in this 101 intro is the idea of combining. So the goal of multi-criteria analysis will be to take additional layers and combine it with this. And the question is, what if one of the input layers has very skewed, or if one or more of the input layers have very skewed data values? So you can think of that as a particularly high average or a particularly low average. And just as food for thought, I've pre-built another layer where 3 of the cells had a value of 10 as the original input. 1 of the cells had a value of 1. And when we normalize that, so you can see that the majority of the study area here is scoring a 1, and a small portion of the study area has scored at 0.1. And if you compare that to the layer we just built a minute ago, this would certainly have a much lower average cell value, although not radically low. In fact, I guess this one comes up somewhere in the middle, somewhere probably just below 0.5, somewhere down around 0.4. Whereas the average of this data set is clearly going to be quite high, up around 0.8 or 0.9. And I'll quickly do the weighted sum on those. So this is the step where you put them together. There's a number of ways to accomplish a weighted sum in ArcGIS, and John showed us last week using map algebra. There's also another tool called weighted sum that accomplishes the same thing. So I'll use that one quickly. So the 2 inputs we want are the max score normalized, which is the one that we built in the example, and then the max score high, which again is also normalized, but just with significantly higher average values. And we're going to give them both. We're going to give them equal weight. So we don't think one layer is necessarily more important than the other. Or we'll leave the default name. We won't worry about that. Go ahead and run that. Again, I'll just quickly change the display to show us unique values. Oh, let me pick another one. We use that one for one of the inputs. I don't want it to be too confusing. Okay, so just visually, if we look at this weighted output, so essentially it took each of the input layers, each of the cells in each of the input layers, multiplied by the weight, so it gave them both the same weight, and added that up. So visually, if we look at the output. This is one of the inputs. This is the other input. This is the output. Even visually we can see that the input exerted more influence in creating this output. And one of the ideas of multi-criteria decision analysis and using this common scale is to sort of put different criterion, perhaps some economics, some scientific. Not to say that economics is not scientific, but I think you get the point. To take things from radically different scales, put them on an equal playing ground. Well, if if one or more of the input layers is significantly skewed or significantly higher valued compared to the others, then we've lost that equal playing ground. And in terms of a possible solution to that, so this is my last piece, and I'm going to turn it back over to John for a real-world example of this. In terms of a possible solution to that, is what's called a value function approach, where instead of doing a linear normalization like we've seen this morning, you actually define a function that helps address that skewing. And I'll just click the PDF and show you graphically from Malczewski's book the idea of what we're talking about. So on the bottom left of this page 121 is a normalization curve that is not linear. That's based more on a function. So I'll turn it back to John, and I think he's going to introduce a data set from the Wilderness Society, that's a real-world data set that has this issue.
Okay. Thanks, Randall. And yeah, if let's switch over to Jen's computer. Jen, are you ready for that?
Yes.
Okay, we're going to switch over to Jen's computer, and I'll further introduce it. But yeah, I think that Randall's, it's hard to give the whole summary of the problem when you only have 4 cells, but when you have a lot more, then it becomes a lot more prevalent. So here's Jen's. Let's go ahead and just take a quick look at this. So here we have, in this case, we're just looking at cells along roads. So we're not looking at the whole entire landscape. But each 30 meter by 30 meter cell on a road has value. Oh, and it looks like she has it summarized by road segments. I'll just turn it over to Jen. She'll take it away. All right, Jen?
Okay. So do you want me to start here once we're summarized by road segments, John?
What's that?
Is this an okay starting point, or do you want to take it back to where it was raster?
No, I think this is a better starting point. Thanks.
Okay. So yes, this is relates to some of the road decommissioning prioritization work that we're doing here in the California office, and this is just on the El Dorado National Forest. It's just some blob of land in the background, and this is our first stab at this modeling approach. So the way this actually works is it's a weighted analysis of 3 data sets that are in question, and so I'm going to show you the histograms of the 3 different data sets that had a number of inputs that went into each of them. So one we can call soil erosion, and this is what the histogram looks like. And so the numbers up here, it doesn't look too bad by looking at it, but we were a little worried about its mean being at 0.29, which you'll especially see when I compare this to the other 2 data sets. So isolation, this was really just a focal sum analysis, similar to a road density analysis, the way you can think about it. And this is how it played out in these road segments. Again, the histogram actually is much better here. The mean is 0.55. We were pretty happy with that. But then the real scary one is when we started to look at stream crossing. So I know it's hard to see because this gray color is pretty faint, especially in this scenario, but our mean is 0.01, and the skew is just entirely over here on this, we'll add, 0.01. So when we were looking at, weighting these 3 together and combining them, we just had a lot of concern over, I guess, the distribution. And so Matt, John, and I, Matt Deep, who I don't believe is on this call today, John Gallo and I sort of came up with an on-the-fly solution that day. I guess I didn't prepare to open that document up, and this isn't well prepared.
You don't need to open that one up.
Okay.
Because, the on-the-fly solution was one of those solutions where we had a deadline, we had a client, a partner that needed the output right away, and so we did a quick workaround. But we knew that wasn't scientifically rigorous. Basically, the workaround was we wanted each layer to have have the same amount of influence as the other. We really wanted to weight each layer the same, but we realized that if we gave them all equal weights, then this one that we're looking at would just get totally washed out. It would have very little influence on the final output. So we looked at, well, what would the weights need to be in order to have the means be the same? And so one weight ended up being like 0.97, and the other weight was a 0.02, and the other weight was a 0.01.
This stream crossing file that you're looking at here, this histogram, ended up, in order to equalize, was 0.97, and then the other two were 0.02 and 0.01. Right.
But then we were able to, Randall, I think I'm going to pop it back to your screen since you have that that diagram up from Malzewski, right?
No problem.
And if you're still there, Randall, are you still there?
I am. Yeah, I just unmuted my mic.
Okay. So it looks to me like there might be. Let's see. Uh-oh, did I just do something wrong there?
I just took screen control again. You should be seeing Malzewski again.
Okay, great. So another way to deal with that, this might actually be the answer for this dilemma, is to do this Malzewski thing that's called the value function, or and I think he has it in italics here, the mid-value method. So in this case, what you end up doing is for that roads data, for that roads histogram, we would end up saying, okay, if the mean value of all these roads values across the landscape is, what was it, a 0.02 or something like that, Jen? We could do something as simple as just say the mean value of each data set is actually what we want to be the mean relative value of the data set. So then what you end up doing is you make a chart like this down here at the bottom. I don't think we have enough time to really go into this. Maybe this is something that Jen, Matt, and I can work on and get back to the team on in a couple weeks. But what you end up doing is you end up making a value judgment as far as what is the relative value of these different things. And so in that case, we would end up saying 0.02 is actually a relative value of a 0.5. And we would do that for a few other points, and then use Excel or some other function that would actually plot a curve that best meets all the points that we plot. And then we would use that curve to then multiply that by our